Welcome to our next video in the series on condensed matter theory. In this video I want to have a look at the tight binding representation of the electronic structure of nickel oxide. And nickel oxide is actually a very nice example because everything works really well for tight binding. We can make perfect descriptions of the electronic structure. And if we measure certain parameters that you have in the tight binding Hamiltonian, interactions between atoms, energy differences between on-site orbitals, then they come out pretty good in agreement with the experiment. But there is one problem. As we will see, nickel oxide on this level of theory is a metal. In reality, it's a very good insulator, which shows you that, our level of theory can do a lot, but as long as we neglect Coulomb repulsion for a certain class of materials, things do go wrong. So nickel oxide is a rock salt structure, so we have alternating nickel and oxygen atoms on a 3D cubic lattice, checkerboard kind of order. Each nickel is surrounded by 6 oxygen atoms. Each oxygen atom is surrounded by 6 nickel atoms. Oxygen sits here and becomes 2-, is therefore a filled shell. Nickel sits here. It has 8 electrons in the D shell, 2 electrons in the P shell. The 2 electrons in the P shell go to the oxygen. Nickel becomes 2+, 2 electrons in the S shell, go to the oxygen. Oxygen is 2-, nickel is 2+, and we're left with 8 electrons in the D shell. So if we do a density functional theory calculation and we downfold to a basis where we include the oxygen P and the nickel D orbitals, then we see that we have here at low energy the oxygen P orbitals that are completely filled, the nickel D orbitals which are partly filled, and we have here a band coming in which would be the nickel S band. We can now have a look at the Wannier functions that we have, and we see that the nickel D orbitals are nice and atomic-like, and then we have the oxygen P orbitals. Now the oxygen P orbitals have these kind of weird tails at the nickel. Here at the center is the oxygen and there is the nickel. And there we should be wary, because when I said that as a basis we only take oxygen P and nickel D, we actually have the nickel 4s that is hybridizing or interacting with the oxygen P. And what we see here are basically the bonding orbitals between the oxygen 2p and nickel 4s orbital. Then we have the d orbitals that point towards the oxygens, they make sigma bonds. We have the orbitals that point in between the oxygens, they make pi bonds. If we compare the nickel Wannier orbitals to the atomic orbitals, and as you see here, the full basis set bands fall perfectly on top of the tight binding model bands, which is short-ranged. Then you see that the atomic wave function is very similar to the Wannier orbitals. The T to G orbitals point in between the oxygens, the EG orbitals point towards the oxygen. So the EG orbital must have a node at the distance where the next oxygen is coming. The T to G orbitals don't have to be 0 at that point, because the radial, the angular part makes sure that you're 0 in that direction to begin with. Now let's have a look at the tails of the oxygen orbitals in a bit more detail. And you can look at the oxygen 2p, the nickel 4s. And if you look internally, the nickel 4s has all these nodes because it's not a 1s but a 4s, so you must have 3 nodes in there. And if you make that linear combination, then you see that indeed you get this 4s character in there. So that's what makes you these additional nodes. Now, instead of making Wannier functions including both the nickel D and the oxygen P, we could have also said, well, we have here 5 bands close to the Fermi energy, we can just make Wannier functions for those 5 bands. These are the anti-bonding band orbitals of the oxygen P and nickel D. And you see now that your Wannier functions have this additional character at oxygen as well as the nickel, D at the nickel, P at the oxygen, and you have a node in between because you are in the anti-bonding orbitals. And we have orbitals that make pi bonds, which we will call the T2Gs, and we have orbitals that make sigma bonds, which we will call EG orbitals. And the notation EG and T2G corresponds to the irreducible representation in the cubic point group. It's something like even and odd orbitals when you have inversion symmetry, but now of course you have the cubic symmetries in your system. And these are then the different labels that you can put on them. Instead of looking at the anti-bonding orbitals, which are at the Fermi energy, so those have a physical implication because those are the low energy states to which you make excitations. We can also look at the bonding orbitals, which are oxygen P-like, so the oxygen sits in the center, but now have tails on the nearest neighbor nickel. Perpendicular to the oxygen P orbital, they are of pi bonding type, so the T2Gs in the direction you are of EG type. And it is these orbitals, these 3 orbitals, with which you can make a short-range tight binding Hamiltonian for these 3 bands. And the same as with these 5 bands, you can make a short-range tight binding Hamiltonian for these 5 bands. Now, so far so good. If you would measure, for example, the energy difference between the EGs and the T2Gs, then you will find that for the local orbitals, that is just the center of gravity of these densities of states, or partial densities of states. That agrees very well with experiment. You can do experiments where you measure hybridization strengths or hopping strengths. Also, those agree very well with experiment. But there is one problem. In our theory, we have states at the Fermi energy. So in this theory, nickel oxide is a metal. If you do experiments, you will find that nickel oxide is a really good insulator with an optical gap of about 3.5 to 4 electron volt. There's nothing wrong with our band structure. It's just that we have neglected, or there's nothing wrong with the parameters and the orbitals in our band structure. We have neglected the Coulomb interaction on its full grand scale. We have made a mean field approximation in our theory. And we have an open D shell in this material. So that's no longer valid. And this is something we will discuss not in this lecture, but in next semester, how to deal with correlated systems with open shells and the physics that happens in such kind of materials. For now, thank you very much for your attention. We see each other later. Stay healthy.